Companies spend millions deploying firewalls and endpoint protection, yet 6 months later, the environment is breached and data is stolen. The board demands to know how the attackers found the one weakness they missed. The answer usually comes down to timing. Traditional defense relies heavily on reacting. Organizations deploy their infrastructure, wait for an incident to occur, and then scramble to patch the vulnerabilities. Attackers operate on a completely different timeline. They systematically analyze the system's architecture, looking for viable paths long before they ever attempt an exploit. While most teams are forced to wait for an attack to reveal their weaknesses, the most resilient systems are built by those who map out their opponent's moves before the first line of code is even written. This structured security thinking is known as threat modeling. It is an architectural discipline executed strictly before deployment and production. The traditional life cycle on the left loops from launch to attack to patching damage. The modern life cycle on the right reorders this into design, threat model, and secure launch. Fixing flaws during this expanded design phase is significantly cheaper. To do this, you have to look at your own blueprint and ask, if I were the attacker, how would I compromise this system? By internalizing this mindset, security moves out of the data center and into the design room, embedding defense directly into the system structure. We can see this in practice by architecting a standard online e-commerce application. Here is our blueprint, containing a customer application, a payment gateway, and a database. Threat modeling follows a strict 4-step process. Step 1 is to understand the system. You identify exactly what assets live inside these nodes. For this platform, we protect customer accounts, payment information, and order history. You also map how information moves between these assets. With the map established, we move to step 2, identify threats. You adopt the attacker's perspective and ask what can go wrong along each data path. You cannot protect a system you haven't fully mapped. Understanding the data flow is the absolute prerequisite to defending it. To categorize the threats identified in Step 2, we use Microsoft's STRIDE framework. S stands for spoofing. This occurs when an attacker pretends to be someone else. In our e-commerce environment, an attacker might use stolen credentials to log in and assume a fake user identity. T is for tampering, the unauthorized modification of data. This could involve altering transaction amounts as they travel to the payment gateway, or manipulating the system logs to cover their tracks. R is for repudiation. This happens when a user successfully denies performing a specific action. A user might claim they never made a purchase. Without proper logging mechanisms, proving otherwise becomes impossible. STRIDE is effective because it categorizes the specific intent of the attacker well before any technical vulnerability is discovered. Moving down the list, I stands for information disclosure, the unauthorized exposure of sensitive data. This happens when sensitive files, like our customer order histories, leak to the public internet. D is denial of service. The goal here is making systems completely unavailable to legitimate users. A distributed denial of service, or DDoS attack, could easily take the customer application gateway offline, halting all sales. Finally, E is elevation of privilege. This is an attacker gaining higher system permissions than they were authorized to have. A normal shopper exploiting a flaw to become a system administrator is one of the most dangerous scenarios an architect can face. If you encounter STRIDE on the CISSP exam, remember its exact function. It strictly categorizes threats, the goal of the attack. Do not confuse these categories with the system's vulnerabilities, or the controls used to defend against them. Step 3 is analyzing vulnerabilities. We now connect our theoretical STRIDE threats to specific weaknesses in our architecture. For example, the threat of spoofing, or account takeover, connects directly to the vulnerability of weak user passwords. This leads directly to Step 4, define security controls. We ask how we can physically stop this specific attack path. We mitigate the weak password vulnerability by requiring multi-factor authentication. To stop the information disclosure threat at the database, we mandate data encryption at rest and strict API security protocols. Security controls should never be guessed or applied randomly. They must be systematically derived from the explicit threats and vulnerabilities mapped in your earlier steps. Reviewing our completed architectural model, we see 4 clear layers: the base system, the data flows, the STRIDE threat vectors, and the applied security controls blocking those vectors. By applying this process, we've identified the critical attack paths of an e-commerce site and assigned defenses to them, all before a single server was provisioned. Let's test this conceptual understanding against a formal CISSP exam standard. What's the primary purpose of threat modeling? A. Conduct penetration testing. B. Identify potential threats before deployment. C. Respond to incidents. D. Perform forensic investigations. The correct answer is B. Threat modeling identifies potential risks before a system goes live. Options like penetration testing or forensic investigations occur after deployment. They are reactive, operational tasks, not proactive architectural ones. Attackers consistently breach networks because they study the architecture and plan their paths ahead of the existing defenses. Security professionals win by doing the exact same thing. By codifying proactive prediction directly into the architectural design phase, you ensure your system is heavily defended before it even exists in reality.